Okay, so till now we have been doing more or less, half the course has started. We have been doing common source amplifier, and I'm pretty sure you guys are bored. So let's do something different, right? Let's use it to do something different. So one of the issues of common source amplifier is, common source amplifier has many issues, but one of the major issues in the context of making an amplifier is, even though you can get decent amount of gain, the gain is not dependent. The gain is directly dependent on the load resistance RL, right? So that is a problem. Why that is a problem? That is a problem because often the load resistance is not in your control. It can be a variable load resistance also. Okay, so if the load resistance varies, then obviously the gain varies, right? So that might be a problem. Another problem is the gain is GM times RL. GM is a function of threshold voltage, is a function of mobility, at least in the simplistic current equation that we have been using till now. Then another problem, the subsequent problem essentially becomes that mobility, threshold voltage, all these things are strong functions of temperature, which means that your gain becomes function of temperature. So what is the problem with that? The problem is, let's say we take the example of a music system, right? You have your favorite music system. You want to listen to your music at a certain volume. So you turn the knob or slide the slider to, you set it at a certain volume. And if, let's say, ambient condition changes, like temperature changes, or you take the same setting to maybe Ladakh or to third desert or something, where the temperature will fluctuate from +40 to -40, the gain will change, which means the output of the volume of your sound will change, right? So this is one example of where having an ambient, where if your gain is dependent on temperature, it can be a problem, right? So this is one simplistic example of an audio amplifier, but you can basically extend the analogy to anything that any electronic system. So whenever you're making any system, any electronic system per se, then you'll have to ensure that the transfer function of the system is reliable. By reliable, I mean it doesn't really change with the whims of the weather. Okay. So clearly, a common source amplifier doesn't fall into that category. If you use a common source amplifier as the way that we have been doing till now, your gain will be dependent on not only the load but also on the ambient conditions. So this is not good. We need to address. Okay, we need to address how we can fix this. So people came up with multiple ways of addressing this, but the fundamental principle of controlling anything is through negative feedback. Okay, so that's what we are going to focus on for the upcoming lectures. Few of the consecutive upcoming lectures, how to develop a system using negative feedback. And you'll see that a gain block has its own place in the negative feedback system. And then we will see that what are the, is there any consequence of putting systems in negative feedback? You'll see that there will be issues with stability. There will be certain other issues that will come up, and then we'll see how to fix those, right? So that essentially is the motivation for the next few lectures that we'll be embarking. By the way, just wanted to have a survey. Is there anybody in this room who didn't take any control system classes in their UG curriculum? And all of you have taken at least one control system class, right? So you know the basics of stability and Nyquist plot, Bode plot, those things. Okay, fine. So we'll use those concepts. I'll go refresh them quickly once, but underlying assumption is that you have already seen this. This is not the first course. This is not the first course where you are seeing those things. Okay. Okay. So let's get started. So if we take the example that I started off with of a music system, right? So you turn on the knob or you slide the slider to a certain pitch, a certain decibel level, and let's say something changes, right? So let's say your music system, again, it's a transfer function, right? Input is some mechanical movement, output is sound. So you have, and maybe you have a knob here that you want to, this looks like a year. Maybe a knob, right? So you can change the knob or a slider or something. You can change it up and down or something you can do. So this has sound emanating from it. And I am sitting here and observing the sound, okay? So let's say for some reason, the sound went up, right? Or even before that, let me take a step back, right? So let's say I have, depending on what time of the day I am, what mood I am at in, I want certain volume of the sound. And I maybe slide this slider. Let's say this is a horizontal slider, right? So I slide this slider on the right to increase the sound, and I see that, and I observe that the volume is too high, right? Then what should I do in order to, in order to get the volume to my desired level? I have to move the slider back, right? So I need to move the slider back, and then the volume will hopefully be at my desired level. And if it's not, then I'll have to adjust the slider again, and I have to keep doing it till I'm happy with the sound that I'm receiving, right? We all agree with this? Okay. So let's say I am, inside an isolated room, right? So let's say I am inside an isolated room, and the speaker is somewhere else. I'm not getting what the exact volume is, right? I have only the information of what I am doing with the slider. Okay, and somebody else is hearing the sound. Okay, so I turn the system on, I put the slider in at a certain setting. Will I know exactly what the volume is and what setting should I set the slider to? No, right? There's no information. I'm not getting any information from the output of the system, right? So this is what we call an open loop control. This particular scenario that I just described is an open loop control where you don't have any output that you are observing. You just assume that I know the transfer function. I have found out the transfer function 3 days back. If I know that I set the slider to 75% to its maximum volume, the volume is so much, and I set it there. Okay. But if, let's say, that because of changes in whatever weather, or because maybe, the music system got damped or something happened, the volume actually changed, I will not have any information to fix it because I am not observing the output. Okay. So this is the problem of open loop control, right? You are not feeding the information, you are not observing the output and trying to correct the output by taking some action at the input side. Okay. But the first example that I gave, where you are observing the output, you are a part of the system and you are observing the output, then you can do something, right? So you know that if I have to reduce the volume, I have to slide the slider to the left. If I have to increase the volume, I have to slide the slider to the right, and I'll be able to adjust the volume, right? So this is a closed loop control. This is an example of a closed loop control. What are you essentially doing? You are taking the information of the output and you are taking a corrective step at the input. Okay. So if we are satisfied with this analogy, then let's walk through the steps that we are intuitively doing. Okay. So what are we doing? First thing is, so step one, I mean, obviously to turn it on and all those things. So I'm not writing them as a step, but the way the feedback is working is as follows. That for step one is you observe the output. Step two is you are comparing your output. Compare the output with a desired output, right? So in this case, you know that whatever is the desired volume level that you wish for, it's in your mind, that's fine. But you are still comparing the sound that you are actually hearing with the level that you're comfortable with, right? And then take corrective action if there's a difference between desired and actual, right? You're happy with this? If you follow these 3 steps, at the end of the day, it might take multiple iterations, but this feedback system through which you are controlling the volume will be set. Okay, and this is a continuous process. It's not like you do it once and set, because something might happen to the music system somewhere else. Then you have to change whatever you are doing at the input side. Okay, fine. So this is essentially these are principles of these are some of 3 of the guiding steps how you set up a feedback system. Now when we say feedback, we know there are 2 types of feedback. One is positive feedback, one is negative feedback, right? The stuff that I mentioned right now is essentially a negative feedback system. Now let me maybe formally introduce why we call this, why we say this is a negative feedback system. The reason this is a negative feedback is it is trying to compare 2 things, right? It is not trying to compare the actual output and your desired output, and it is trying to ensure that the difference between them reduces. Ideally, if you know what is your desired output, and you always know what is your actual output, in your mind, you are making a subtract, you are comparing them. And how do you compare? You subtract one from another, and you are trying to ensure that the difference goes to 0. If you set the difference to 0, which means your actual output is equal to your desired output. Okay, so then why is it a negative feedback? This is negative feedback because let's say your system is working fine, right? So you have done all these things, the system is working fine, and for some reason the volume goes up because of things not in your control. Maybe let's say for some reason your volume goes up. So your volume, let's say, goes up. Okay, if your volume goes up, then you observe that the volume went up. What will be your action? You have to basically, in this, a mechanical action is move the slider to the left, right? So you are moving the slider to the left. So what will that do? The input of the speaker is again a electrical signal. The input of the speaker will go down, right? This will go down, which means the output will also go down, right? So any disturbance in this loop, the loop is trying to negate it. Once the loop is set, if you try to force any disturbance, the loop is trying to mitigate it. It's negating the disturbance in the loop once the loop is set. Since it's trying to negate, the feedback loop is trying to negate any external disturbance. It's a negative feedback. Okay. So in any system, if it's in a feedback, the way to understand whether it's negative feedback or positive feedback is that, you can, once you know the components of the system, you inject a hypothetical excitation in some direction, right? In this case, I assume that the volume went up. Then I went around the loop and tried to figure out, is the loop action in such a way that it is trying to reduce that injection or it is trying to increase that injection? If it is in the sense of the negative feedback is such that it's trying to reduce the injection, then it's a negative feedback loop. Sorry, if the sense of the feedback is such that it's trying to reduce the injection, it's a negative feedback loop. If the sense is it's trying to increase the injection, then it becomes a positive feedback loop, right? I mean, a simple scenario in this case, how the loop can become positive feedback is, let's say you didn't know that which side of the, I mean, if you move the slider to the right, the volume increases, or if you move the slider to the left, the volume increases. Let's say you don't know that, right? So in that case, let's say you assume that if you move the slider to the left, the volume increases, right? So then, do you think it's a positive feedback loop or negative feedback loop? Then it becomes a positive feedback loop. How do you know? Because if you increase, you observe that the volume increased, right? So in order to reduce the volume, you still want to reduce the volume, you move the slider to the left. You move the slider to the left, but unbeknownst to you, it increased the input at the input of the speaker. So the output of the speaker also went up, right? So this becomes a positive feedback loop, right? So since you are smart enough, you know that what to do. You know that, okay, maybe the sign of the loop was not correct. So you will do the corrective action. Then you will update your thoughts that, okay, instead of moving the slider to the left, I have to move the slider to the right. And you are all good, right? So, but when you have to make a system where a human being is not a part of the loop, then you have to make this process automated, right? So that's where design comes into picture. So firstly, you need to know when you are designing, you need to know whether the sense of the loop is correct or not, right? So which means you'll have to find out a way of putting the system together in which the system is actually negative feedback, and then go and decide the component values, architecture, and so forth, right? Okay, fine. So this is as far as heuristic examples are concerned. So let's dive into our electrical examples, right? Okay, so now we want to make the context with which we started was we want to make an amplifier, right? We want to make an amplifier in which where things are stable, right? Things are stable with ambient conditions. So let's take this example. Let's stick to this example for a couple of minutes more. So let's say let's say it's an open loop system, the ones that we started off with, where you are not observing the output, and maybe the speaker that you are using is a function of humidity, right? So in the rainy day, it doesn't perform too well. In sunny day, it performs well, and all those things, right? So you turn on the volume, you don't know exactly what volume will come out or what sound will come out, right? And if you have no way of if you have no way of closing the loop, that is, you are not observing the output, you are not in control of what the output volume is, which means this is your system is strongly influenced by the ambient conditions. But in this case, if you close the loop, right? If you close the loop, do you think this is a better way of controlling output, in the sense that, let's say, the humidity changes, your speaker starts malfunctioning in some certain way, right? So is there a way of fixing using negative feedback loop? So let's say the speaker, for some reason, in a humid condition, doesn't give you enough volume, right? And you are using negative feedback control. Can you restore the volume? Yes, you can, right? Because you have another setting, you can move the slider to a slightly higher setting, right? So this type of a negative feedback can give you stability in terms of the output, right? The output level that you want can be made invariant to temperature variation, invariant to ambient variation. Okay, so that is why negative feedback, you seldom design systems without negative feedback, simply because you want the experience of using whatever network, whatever circuit you are making reliable. Okay, fine. So essentially now what we would like to do, we would like to make an amplifier using negative feedback because of all these good things. Okay. Okay, fine. So let's say you have an amplifier. Let's say we have an amplifier of, let's say this is a common source amplifier with a transfer function A0 by 1 plus S by P1, 1 plus S by P2. And common source amplifier also has a 0, right? So I am using block diagram. We'll couple of this lecture will be using block diagram. Then we'll replace block diagrams later on. Okay, and let's further assume that A0 is positive for the time being, right? In a common source amplifier, your gain is negative, but let's keep it positive for the time being. We can make it negative later on. Okay, and the hope is if you have an input and I have an output, and I am observing the output here. Okay, we want V0 to be equal to some K times Vi. This is our goal. Right, and we want to do it using negative feedback. Okay. And let's say K is equal to, K is not 1000 or something. Let's say K equal to maybe 5. Okay, but the key thing is that we want this to be very stable. We don't want this to be a function of RL. We don't want to be a function of temperature, which means we don't want K to be a strong function of GM, right? Because GM is a function of threshold voltage, GM is a function of mobility, which is a function of temperature, right? So K must be independent of GM or RL. Okay. Okay. So now in a circuit, you have only so many components to play with, right? You can use a transistor, resistor, capacitor, inductor, and all those things, right? So if we have to hit a certain gain K, we have to use any one of these 3 or 4 components that we have, right? So, and as it turns out, all the components are functions of temperature, right? So this becomes a problem. This becomes a problem because if we desire a negative feedback system where something is stable, then we need to make it. I mean, it's not like I just write a transfer function in the piece of paper and it will get done. We have to implement it, and our hands are tied because the things that we can play with all vary with temperature. Okay, but there is a solution, and the solution is as follows. Let's say I ask you to make a let's say I say that I want V0 to be equal to 1/5 Vi. Okay, can you think of a way of making V0 equal to Vi by 5 in a very stable way? I mean, this 1/5 should not be a function of temperature. You can use a resistor divider, right? So you can use a resistor divider. Let's say this is Vi. You make this R, you make this 4R. This voltage here will be Vi by 5, correct? And let's say temperature change and R became R plus delta R. This R will also become R plus delta R. This ratio still remains as is, right? So there are certain assumptions when I wrote this, and the assumptions are, if I call this R R1, this is R2. R1 and R2 are made up of similar material, or rather same material with same temperature coefficient, right? And they are also probably, I mean, not probably, they are identical to each other in terms of their thermal characteristics. Then only this ratio will become independent of temperature, right? So the good thing about IC design is you can make components which are quite similar to each other, right? But the bad thing about IC design is these components can vary a lot. Individually, one component value can vary by easily plus minus 20%, right? However, if all the components vary by plus minus 20% in a similar direction, then the ratio becomes independent of any change, right? Okay, so that's good. So we can use this principle. So basically, the principle that we are trying to, I'm trying to motivate here is that ratios of similar elements. Are independent of ambient change. But the problem is, moment you take ratio, your output is obviously lesser than the input, right? But the problem is, so this is good thing, this is good. But the bad thing is, ratios are less than 1. So if you want to make a gain, gain amplifier, right, where the output is supposed to be higher than the input, then only taking a ratio will not suffice. Okay. Now the bad thing about an open loop, let's say amplifier. So the bad thing of a common source amplifier or a open loop amplifier is open loop amps are dependent on ambient conditions. But the good thing is, gain can be greater than 1. Okay. So this is for open loop amplifier. Okay, so now you see that we have two types. We have a problem here because in one case I am getting good gain, but the gain is not reliable. In another case, we are not getting gain, but whatever we are getting is very reliable. So we need to marry these two, right? So that we ensure that we get the good things of both these systems, right? So let's see if we use this, if this is possible using negative feedback. Okay, so what? So let's say we have RL, we have VI, V0. So the first thing that we said in negative feedback was you observe the output and you compared with it with the desired output, right? So which means you have to find out, you have to take a difference between the desired output and the expected output or actual output, right? So actual output is, I mean, we know that we want the output across RL, we want the voltage output across RL. So actual output is V0. So and what is desired output? In our case, what is the desired output? K times Vi, right? Desired output is K times Vi. Okay. So once you identified what is your actual output and what is your desired output, you have to go and find out a way of comparing them. In the music system case, you are in charge, you are listening to the sound and you are comparing it and taking action. But if you are making an electrical system, you have to do that electronically, right? So what is the easiest way to compare two voltages? You basically take a subtraction, right? You make a subtraction, right? So let's say I compare by making V0 minus KVI, and I name it VE. VE stands for error. Okay, so let's say I find a way of observing that error voltage. So again, if I go back to that example of music system, what did we do? Once we knew the error was my expected volume minus the actual volume. We were taking a decision to reduce that error, right? So what is the next step? The next step will be set up your system to drive VE to 0. Right? So if I can set up a system which drives the error to 0, then V0 will be equal to KVI. Correct? Okay, fine. So the problem, okay, so if we do this, this is all good. But the problem is, in order to do this, you'll have to ensure that you have KVI in the first place. Correct? So you have V0, no problem with that. That's a voltage across the resistor. But if you have to compare with something else electronically, you need to have that something else. In that something else is KVI. But KVI is something that we desire anyway, right? So if we had that, there's no point in building anything. So we don't have this, right? So then what can we do? We can do something. We can do something smart about. And so what people did was to say that, okay, so ultimately we want V0 minus KVI. We want to drive this to 0. We don't have KVI, but can we do this? Can we divide by K and say that we'll drive V0 by K minus Vi to 0? So can we do this? Where if we can do this, this is exactly same. This will have exactly same effect as V0 minus KVI tending to 0. Right. So essentially what we are saying is that our error voltage should be not V0 minus KVI. Our error voltage should be V0 by K minus Vi. And why is this an easier implementation? We had Vi initially also. Right. We can get V0 by K reliably, because reducing a voltage reliably is an easier task than increasing a voltage reliably. We can use some sort of voltage divider to reduce the voltage, and K can be independent of, because K is a ratio of voltages, the ratio of voltages across resistors, or rather K is the ratio of resistors, and the ratio can be independent of ambient conditions. That we have already seen, right? So this is doable, right? And so V0 by K we can get. Okay, fine. So and drive this new VE to be towards 0. Okay. So let's say we embark on this journey. So this is V0. So I need V0 over K. So how can I get V0 over K? Same thing, right? We put a resistor divider. And let's say this is K minus 1 R. This is R. So what will this voltage be? It will be V0 over K. Okay. Okay, fine. So by the way, do you think if I go back to this resistor divider thing and say that, let's say I have a load resistance connected here, some RL. This ratio will be independent. I mean, the ratio will be independent of, or the ratio will be 1 over 5, or will it be different? It will be different because RL will load, right? So in this case, whatever the feedback system is, ultimate goal is to ensure that the RL doesn't load. Okay, and that is something you should keep in mind, right? We will see how we can generate, how we can go about addressing that issue of loading issue. Okay, okay, fine. So this is VI, this is VI, and we have V naught over K. So we want to generate VE, right? Because if we don't have the difference, if we don't have the error, we cannot use that information to drive the output. So if I have block diagrams and in the block diagram I have everything available, then I can say I can generate VE by simply subtracting VI and V naught minus K. So by the way, here I wrote VE as V naught by K minus VI. See, in the absence of anything, I can as well say VE is equal to VI minus V naught by K. If I drive that to 0, that is also fine. Right. So at this stage, we will not make any distinction between whether the error voltage is V naught over K minus VI or VI over V naught minus K, because we don't know enough. So once we set it up, then we'll see. So let's say this is VE. In this case, VE is equal to VI minus V naught over K. So we have this. So we have to put something here. We have to put something here, which essentially can drive V naught to our desired value. Okay. So now let's go back and try to figure out what the transfer function of this block should be. Okay. So let's say this has a gain of K. Everything is electrical, and let's say we are all operating in voltage domain. So when I say A, I mean that there is a voltage gain of A. Okay. So let's say I have a voltage gain of A. So then we can put the system together. Then we can put our analysis at and then figure out what this A should be. Okay, so let's do that. So now what is V naught? If I, in terms of VE, V naught is A times V, and this is A times VI minus V naught over K. Right? So okay, so if I manipulate the equation, what should I get? I will get V naught over K to be VI minus V naught by K. Is that correct? Yeah, correct. So which means that V naught is A times VI minus A times V naught over A. Correct? So why am I writing in this form? Is because if in this case, if A tends to infinity, right? If A tends to infinity, it seems like V naught tends to A times VI. Correct? You can write it in a more traditional form also, and the traditional form is expressing V naught in terms of VI, that is left hand side V naught, right hand side VI. So if I write it in that format, what should I get? I should get V naught 1 plus A by K is equal to A times VI. Means V naught is K. In other words, this is K times or I can write it in this form, divide by A. Okay, so in this case also you see, if limiting value of V naught when A tends to infinity is equal to K times VI. Okay, so So essentially, the goal is to make an amplifier A and put it here such that the gain of A is infinity, right? So, but does it need to be reliably infinity? No, right? All I need to ensure is that A is very high. Why? Because ultimately, let's say A is finite, right? If A is finite, what is the error between the expected output and the desired output? So VE is, expected output is K times VI, and sorry, expected output minus actual output. So K times VI minus K times VI by 1 plus K by A. So what is the error? So this is K times VI, I take on. So this is I should not say VE is not this, right? So this is like delta V naught. That is the error in the output. So that's how we have defined VE was something else, right? So this goes. Or in other words, percentage wise or the ratio wise, so delta V naught by K VI is approximately equal to K by A. This is if K by A is much less than 1. Okay, so as you can see that the error that you are going to get is inversely proportional to the gain, right? This is a voltage error that you are going to get. It is inversely proportional to A. And if you, let's say, want 1%, you are okay with 1% accuracy or inaccuracy. So all you have to do is to ensure that K by A is 0.01. Right? If you say that I am okay with 0.1% accuracy, then you have to design your amplifier in such a way that K by A is 0.01, 0.001, right? But let's say instead of, which means that, okay, so let's say what I'm trying to get at here is, if let's say we want 1% accuracy, we have to ensure that K by A is less than 0.01, right? So let's say you design for 0.01 and as it turned out that it becomes 0.005. Is it a good thing or a bad thing? No, what I'm essentially saying, okay, let me put it in this way. So let's say we want, which means A should be greater than 100 times K, right? Or if we, let's say, want a gain of K to be 5, so which means A should be, your target design should be, A should be greater than 500, if K equal to 5. Okay, so you designed your amplifier for a gain of 500. And let's say for some reason, the amplifier gain in some good day went up to 1000. Is it a good thing or a bad thing? Bad thing in an open loop system. In this case, what do you think is going to happen? What is going to happen to that error? It is going to reduce, right? So it's a good thing or a bad thing? It's a good thing, right? So essentially, now you are not constrained with a precise value of A. Your constraint is A has to be large enough, larger than something, right? If you want to make a precise gain of A, or let's say if you want to make a precise gain of 5 using a common source amplifier, one might say that I will set the GM to some value and RL to be 5 by GM, right? In a common source amplifier, my gain is GM times RL. I ensure that, I mean, whatever GM I get, and I choose a value of RL which is 5 over GM. Then I should be able to get a gain of 5. But that gain will not be reliable because my GM might change, RL might change, ambient conditions might change, and that gain can fluctuate. So in an open loop system, you are trying to hit a precise value of gain. But in a closed loop system, you are not trying to hit a precise value of gain. Granted, you need more gain. Instead of 5, now you need a gain of 500. But as long as you can hit a gain above certain level, you are good. The precision requirement goes away. Okay, does that make sense? Okay, fine. So that's why that's why let me go back to this good bad thing. The open loop system and open loop amplifier, you can hit gain of more than 1, but it is unreliable. Right? In a ratio, you can get the reliability. So you can mix you can basically marry these two conditions and set up a system in such a way that you get a gain more than 1 and also you get good reliability, good reliable gain, right? Okay. And the other thing that we can observe here is that your gain, or rather the error is inversely proportional to the gain, right? Since the error is inversely proportional to the gain, then as long as you can keep the gain to be high enough, you are good. Okay. Okay, fine. Any questions till now? Okay. So let's say when we were setting up this system, I mean in this case, you might have noticed that I made a change of VE, right? Here the VE was V naught over K minus VI. I made VE to be VI minus V naught over K. Right. So let's say if it were that, what would have happened? Which means I had to change the signs here. So this should have been minus. This is plus. Okay. So if we had changed this, if we had started off with a sign similar to what I am showing right now, so what would have happened? What do you think would have happened? Will the loop still work? It will work. Okay. So why will it work? How would I know whether the loop will work or not? Difference will be same, but is the sense of the loop correct? I mean, in the sense that if I go back to the first example, right? So you didn't know which side to move the slider to, right? So if you move the slider in the wrong direction, you are still taking an error. You are still observing an error. But if you move the slider in the wrong direction, are you increasing the error or reducing the error? You're increasing the error, right? So in this case, if we use the same analogy, so we need to see whether if the sign of the loop is, we don't know, right? If we are not aware of the sign of the loop in the first place, so we have to have some mental test to figure out is the sign fine or not, right? So what is the mental test? The mental test is in a negative feedback loop. In a negative feedback loop, the loop action should be always to negate an excitation in the loop, right? So that is the main core principle. So hypothetically, you can choose any point in the loop and give an excitation. The voltage amplifier, so you can give a voltage excitation. So right, so let's choose a point, right? So let's choose this point. Let's choose this point and say that the voltage goes up for whatever reason. Okay, so that voltage goes up. So what's going to happen to VE? VE will increase, right? A is positive because that's what we have taken. So if A is positive, what's going to happen to V naught? V naught is going to increase. What's going to happen to the feedback voltage? Let's say this is VF. What's going to happen to VF? It is going to increase, right? So as you can see that the loop is not trying to negate the excitation. In fact, it is aiding the excitation in the direction in which it was operating. Correct? So do you think it's a negative feedback loop or a positive feedback loop? It's a positive feedback loop. So what is the fix? Change the sign, right? So just change the sign. So if you change the sign, then you know that if you go around the loop now, let's say I have the same excitation here, VE is going to go up or down. It is going to go down. This is going to go down. It's going to go down, and you can see that the loop is trying to negate the excitation that we had or the disturbance that we had injected. And this injection can be anywhere in the loop, right? you can as well start off from V0 and then come back at V0 and see whether the excitation or the disturbance is getting negated or amplified or aided. You can start off at VE, it doesn't really matter because a loop is a self-correcting system. Right? So you can start anywhere in the loop. You don't have to consider VI. Just like in the cases of output resistance and all, you assume VI to be shorted and you do it. Yeah, we generally do all the analysis. Similar, I mean, the use of VI is not necessary, but you can also keep it. It doesn't really matter because we are not doing an exact analysis. We are trying to figure out the sense of the loop. Okay. Okay, fine. So this is good. So one more piece of jargon. So this difference, this ratio that I talked about, the error at the output voltage divided by the error at the expected, or rather the desired output. So error at output by expected output is called steady state error. This is at obviously when the system has settled, right? So under steady state, it's called steady state error. Okay. Often you will hear terminologies that my amplifier has 10-bit accuracy or might have like 4-bit accuracy. So what that essentially refers to, the context, I mean, it refers to multiple different things at a time. And the 10-bit or 11-bit or 4-bit or 15-bit, whatever we say, bit means we are referring to something in digital domain. Right, but what are you referring to a digital domain in analog? In an analog circuit, we are essentially referring to the accuracy of an ADC. So what I'm trying to get at here is, so let's say you want what is an ADC? An ADC is a way of sorting your voltages into multiple bins. In the sense that, let's say I have a voltage supply of 1 volt. And the ground is 0, and you have an input voltage of, let's say, 0.49 volts, right? So what an ADC is, when I say I have a, let's say, when I say I have a 10-bit ADC, what I'm essentially saying is I am dividing this 1 volt to 0 volt, this 1 volt range into 2 power 10 equal size spacings, right? So I'm dividing this into 2 power 10 equal size spacing, and I'm trying to figure out within which of this gap this 0.49 volt resides, right? So let's say it resides somewhere here, and I assign a bit code to each of these spacing, right? So it goes from 0, 0, 0 to 1, 1, 1, right? So this will probably be some 0, 0, 0, something 1, 0, 1, 1, something like that. So it's basically a sorting algorithm to figure out where you reside. So in this sorting algorithm, the most important thing is to first figure out which the levels should be very accurate. If the levels keep on moving, then your sorting will not be correct, right? The bit code that you are going to get will be different each time you apply some voltage for the same voltage, right? So that's not good. So which means that this reference levels, right, have to be very accurate. So that's why this, since this is a measure of accuracy, when I say that, let's say your steady state, your amplifier should have an accuracy of 10-bit, what I'm essentially saying is that it should have an accuracy in such a way that the difference of these bits, that is, in this case, the difference of the bit is 1 volt by 2 power 10, right? So this difference, which we call LSB, right? So this the amplifier, the steady state accuracy of your amplifier should be such that the error is less than 1 LSB or half LSB, right? So that's what the jargon means. We're not going to use this jargon in this course, but you will keep on hearing these jargons once you move to the industry. So you should do that calculation at the back of your mind, what it means when we say that 10-bit accuracy or 4-bit accuracy or 11-bit accuracy, right? Okay. Okay, fine. Any questions till now?
Oh. That 10-bit accuracy is said that after getting the error or
this is with error. So because you are never going to get an error of 0, right? In order to get an error of 0, you need infinite gain. That you are never going to get.
10-bit is the effective number of bit or total number of bit?
It's the effective number of bit. I mean, here we are not doing ADC, so they are same, right? So, but ultimately it's a effective number of bits. Okay. Any other questions? Okay, fine. So one question that can, if you start thinking about it, you can that might arise in your mind is the only amplifier that we have done till now is a common source amplifier. And a common source amplifier, the gain is negative, right? So essentially, in our case, the gain is minus A. So if I use the same loop and with a negative gain, do you think the loop is in positive feedback or negative feedback? It's in positive feedback because again, we can go around the loop. Let's say we give excitation here, the disturbance is going up. So the output V0 will go down, Vf will go down. And when it goes through that difference block, it's going to the negative terminal. So it's going to go up. Correct? So which essentially means that we'll have to change the signs of the difference taking block. Okay. And I'm sure you have seen this multiple times before. So this guy is essentially the block diagram of an op-amp. Okay, so this summer plus a gain block in the proper with the proper signage is essentially an operational amplifier. And when we put this operational amplifier in negative feedback, some great things happen, right? One of the great things that happens is what happens to VE if let's say A is infinity. What should be VE? VE will be tending to 0, right? Because ultimately VE is what? VE in this case, you can see here. Vi minus V0 over K. If A tends to infinity, right? If A tends to infinity, then V0 actually becomes KVI, which means VE tends to 0, right? So the only thing in a loop, if a loop is working properly, you cannot start the analysis of the loop. I mean, in principle, you can do the analysis anywhere, but let's say the loop is not working properly. The first thing that you have to go and check is whether VE is sufficiently low. It will never be 0 because you're never going to get infinite gain, but VE is sufficiently 0, right? Sufficiently close to 0. And if it is not, what will it imply? It means that the gain of the loop is not high, right? So let's say, again, I said that let's say you wanted some steady state error of 1%, which means you had to design for A of 500. So since you had to design for A of 500, you can obviously go and check the output and see whether you are getting gain of 500 or not. If you are not getting, then you have to go and fix something. What are you going to observe? You are going to observe what is happening to VE. Is VE sufficiently close to 0 or not? If it is not, you have to go and change the amplifier. Okay. So reason we focus on VE, so let me draw a cleaner block diagram. The reason we focus on VE is, do you think V naught is a strong function of A? Yes or no? Is it a strong function? I mean, is it a linear function of A? Why? Under steady state condition, what is V naught supposed to be? It's KVI, right? It's not a function of A under steady state, right? Should not be, right? Because V naught is supposed to be K times 1 by K times Vi times 1 plus K by A. It's a function of A, but it's a pretty weak function of A, right? If A is sufficiently high enough, then it's not at all a function of A. That's the whole purpose of negative feedback, right? If V naught becomes a strong function of A, then negative feedback is of no use, isn't it? It becomes like an open loop amplifier. Because all we need to, the reason we are doing all these things is because A is not very accurate. Okay, so V naught is not a strong function of it. Fine. So in essence, if we have done a decent job in designing the loop, and Vi is something like this, V naught will probably be approximately 5 times of this. This is, let's say Vp, and let's say this is 5 times Vp. Not to scale, but you get the idea. So if A tends to infinity, or if you change A, which part of the loop or which voltage in the loop will get affected linearly? Or linearly as in, I mean, or let me rephrase, which voltage in the loop is a strong function of the gain? Between the resistors, this one. So this is V naught over K, right? So if V naught is not a strong function over of A, V naught over K is also not a strong function of A. So it's not V naught, it's not that. What remains? VE, right? So what is VE? VE is, we saw, right? We did this thing. VE is what? It's essentially V0 by A, correct? So VE is, or in this case, V0 by minus A, right? So VE is which is K times Vi by A plus K, correct? Minus, right? So if A is much higher than K, this is approximately equal to minus K times Vi by A, correct? So VE is a strong function of A. If you change A by a factor of 2, if we increase the gain by a factor of 2, the error voltage, or not the error voltage, the error at the input of the amplifier goes down by a factor of 2. Correct? So the key point in your negative feedback loop to figure out whether the amplifier is working properly or not is to check the error voltage, because that is a strong function of it. Okay. And since you are trying to figure out whether whether your loop is operating properly, which means that you have to get sufficiently large gain, which means you have to find out a way to evaluate in the loop whether your design is working properly. And for that, you have to go back and check the error voltage. Okay. Okay, fine. Okay. So another critical thing to understand is that even though we wanted, I mean, in this case, these voltages, these errors is not inversely proportional to only A, it's proportional to A by, inversely proportional to A by K, right? So this is Vi by A over K, right? So why not A? Why A over K? And the reason for that obviously comes out mathematically. And the reason is also evident from the block diagram representation of a negative feedback. And the block diagram representation is this, right? So if you have So in this case, we know that V naught over Vi is GH by, sorry, G by 1 plus GH, right? This is also often referred to as 1 over H GH by 1 plus GH. The reason it is referred to like that is because if this guy GH tends to infinity, then the output tends to 1 over H. Okay, so this is essentially the desired transfer function. 1 over H is a desired transfer function that you get when the loop gain, this thing GH is often called the loop gain. The loop gain, when the loop gain tends to infinity, then whatever output you get is the desired output. That is one way to go ahead and analyze the negative feedback loop. You assume that the loop gain is infinity. If the loop gain is infinity, then whatever output you get is the desired output, right? So 1 over H is the desired output. Now, so let's say I have to go ahead and figure. Let's say I don't want to do this bunch of maths, right? Even though it's a simple system, I don't want to do this bunch of maths. I need to figure out what will be V naught over Vi if GH tends to infinity. How should I go about? How should I start analyzing this? So what do I know about a negative feedback system if it works properly? Error is going to 0. What is the error voltage here? VE. Right? So VE should go to 0. If it goes to 0, so this guy has to go to 0. Right? That is the only thing that I know. I mean, I don't know what the transfer function is. If I give you a new circuit, you don't know what the transfer function is supposed to be. You don't know anything. But you know one thing, if the negative feedback works properly, the error voltage has to go to 0. If I can figure out which node in the network is pointing to the error, all I can do is start from there, right? Start from there, assume that error voltage goes to 0, and then work backwards. Because if in this case, if the error voltage is going to 0, and this terminal is Vi, what is this terminal? It has to be Vi, right? If this is Vi, then only the error voltage has gone to 0. If this is Vi, what is going to be V naught? Yeah. Correct? So if the loop works properly, your V naught has to be Vi by H. Now, why did I go backwards and why didn't I go forwards? Yeah, right. So essentially, the forward function, the forward transfer function is, one might as well say that V naught is VE times G. If I know what is V naught, if I know what is VE, then I know what is V naught, which is mathematically true. But the issue is when you are dealing with infinity, right, when you are saying the loop gain is infinity, a limiting value of infinity times a very something which goes to 0 can be also be finite. Right? So you cannot precisely find out what V naught is if the forward transfer function is infinity and you also go in the forward direction. So negative feedback loop always best analyzed in the reverse direction, right? You go backwards, you walk backwards, you never walk forwards. Okay, again, very critical when you will be doing your design at the back end of the course. So there will be negative feedback. You have to figure out if the loop is working properly or not. Always walk backwards. Okay. Now, this is a simplistic loop. Okay. But okay, even before I proceed, so what is this loop gain and how do I figure out what is a loop gain, right? So if you have to find out using simulation, right, and not write down equations and all, what should I do? What the loop gain essentially seems like, if I have to find out this loop gain is independent of Vi. Right? It's a property of the loop. It's the product of the transfer function of G and H. It doesn't really depend on where you apply Vi. So if it doesn't depend on Vi, I can as well remove Vi. Correct? So I can desensitize Vi. So Vi can go to 0. Okay. And if you think about it, what is the loop gain? If let's say I apply an excursion here, let's say I apply anywhere in the loop, let's say I start off from here and I apply an excursion, let's say I break the loop here and I apply some test voltage. So this voltage will be G times V test. So this voltage will be GH times V test. So this voltage will be minus GH times V test. Right? So it looks like, and I call this return voltage. So this looks like if I break the loop physically and observe the ratio of the return voltage and the voltage that I had applied, negative of that is the loop gain, right? So essentially GH, or let me just call this loop gain. Negative of that. Okay. So in a simplistic block diagrammatic representation, you might wonder, why do I bother about taking the loop and all these things? The reason we bother about this is because when we design circuits, it's not particularly apparent which is G, which is H. And also it's not always particularly apparent if G and H are also independent of each other. So the whole game is to find out what is G, what is H. Sometimes you will see that you will not even be able to find out decisively which is G, which is H. But you need to figure out what the loop gain is. You are not particularly bothered about exactly what is G, what is H. You are bothered about the product of G and H. Okay. So that's why you need to figure out a way of getting what the loop gain is. This is also abbreviated as L. Getting what the loop gain is from a loop. I mean, it will be intuitive. It will be all, you can always figure out whether it's a loop or not, right? That will be pretty evident. But what the loop gain is, you have to find out using some analysis, right? The analysis is you have to break the loop somewhere, apply an excitation, and find out whatever comes back. The ratio of whatever comes back and whatever you applied, negative of that, is the loop gain. And as you can readily see, the loop gain is a very important parameter, because ultimately the loop will work as long as the loop gain is very high, right? It's not the gain, it's not G, it's not that A, it's A over K, right? Or A times K or A over K, depending upon whatever, how you define K. So in essence, the whole purpose is to make the loop gain really high, right? So we'll stop here and we'll start off in the next class.